SwayamPrabha. Digital India. Educated India.
Hello, welcome to Basics of Noise and its Measurement. Today is the last day of the second week of these lectures, and in the earlier part of this week what we have essentially done is developed the 1D wave equation, also developed its generic solution, and using that generic solution we have been able to interpret the physical meaning of this constant c which appears in the wave equation. And we explained that this c actually indeed represents the velocity of sound as it propagates through an elastic inviscid medium. What we are going to do today is cover two important concepts, and these concepts are also important because as and when you will be learning more about sound related measurements, these concepts will come in handy and they will be very frequently used. These two concepts are complex time signal and transfer function. So both of these are important concepts. They are not very difficult to grasp, and I will try to explain them and also help you understand their physical significance. And that's what we are going to do today. So the first concept which I have mentioned is known as complex time signal, and essentially it is a mathematical concept. It's a mathematical concept, and then we actually interpret it in the real world and then relate physical quantities to it. So we'll discuss this. So this is complex time signal. So what does it mean? First thing is that it represents a mathematical number which changes with time. It changes with time. So it's a series of numbers in digital domain, or if it's an analog signal, it changes continuously. So it's a time signal. It's a signal which changes with respect to time. And the other feature of it is that it is complex. So if you have suppose a number 2, it's a real number. You have a number 3, it's also a real number. -5, real number. Pi, real number. But these numbers, this time signal, it can be complex in nature. So it may have it can have an imaginary component as well as a real component. And because of this, it is known as a complex time signal, and it varies as a function of time. So a very generic representation of this complex time signal is like this. So you have x e to the power of s t. So this is a complex time signal. Okay. Here x can be complex number. So it can have a real as well as an imaginary component, and then s can also be real complex. This x bar is actually a complex number, and it is actually referred as complex amplitude. Okay. So both x bar and s both are complex numbers. X bar is known as complex amplitude and s is known as complex frequency. Complex complex frequency. So a complex time signal has two complex numbers embedded into it, complex amplitude and complex frequency, and T is time. T is time. So you can have complex pressure, you can have complex voltage, you can have complex current, you can have complex velocity, and all these time signals could be complex entities. But if you want that entity to be mapped into the actual pressure or actual velocity or actual, then you take its real component. So real, excuse me. So suppose this XEST represents complex pressure, then lowercase xt will represent real, actual physical pressure, and that will be real of x bar E S T. The other thing I wanted to mention is this S is complex frequency, so it can have a real component sigma and an imaginary component omega, and J is equal to square root of minus 1. Okay? So it's a square root of -1. So the real component is sigma and the imaginary component is omega. So let's look at an example. So consider that x bar, as I mentioned, it is a complex number, so I can assign it any value, and in this case I am going to call it as 4 e to the power of j pi over 4. And then my complex frequency I am going to choose, and in this case its value is 1.1, there is nothing significant at least currently, plus 5 times j. Okay. So then the complex time signal will be x times e to the power of st, and the real time signal will be xt will be real value of x bar e to the power of st, which is equal to real of 4 e j pi over 4 times e to the power of st, so minus 1.1 plus 5 j times t. Okay. So this is equal to real of 4 e to the power of minus 1.1 t. What I am doing is I am separating complex and real parts, separating them out. So this is one component. Where did I go? Sorry. So times e to the power of j, and then I take pi over 4 from this one, and then 5 plus 5 t from here. Okay. And this is entirely real, so I can take it out. So it is 4 e to the power of minus 1.1 t times real component of e to the power of j pi over 4 plus 5 t. Now we know that e to the power of j theta equals cosine of theta plus j sine of theta. So I use this into this. So what I get is 4 e to the power of minus 1.1 t times real of cosine pi over 4 plus 5t. So this, just to make it clear, this is 5t plus j sine of pi over 4 plus 5t. Okay? And this is nothing but 4 e to the power of minus 1.1 t times cosine of pi over 4 plus 5t. Because this is the real component, this is the imaginary component. So I take this, I do not take this one. So my xt is the real component of that complex time signal, and its value is this. So now what I am going to do is give you a physical interpretation of some of these numbers. But before I do, what I will do is I will actually plot. So what you see is that you have this term here, and then you have this term here. Okay? So what I am going to do is I am going to plot. So on my x-axis it will be time, and on my y-axis I will plot some magnitude. So first I am going to plot this thing. So at time t is equal to 0, this value is 4, and it goes like this. Okay? So this thing is called envelope. Of xt. Why is it called envelope? Because the whole function x cannot go beyond this green curve, and the actual curve will actually do this. It will do something like this. Because there is this pi over 4 difference here, the actual curve, this is the red curve, does not touch the green curve at x is equal to 0. If there was no pi over 4 in this case, then it would have touched it. But because of the presence of pi over 4, it does not touch it. And then it will be important to make some observations. So what does this tell? That 4, it corresponds to envelope's maximum value. Where did this 4 come from? It was a part of the complex amplitude portion. It was the part of complex amplitude portion. Then what else? Pi over 4, it corresponds to phase of signal. Phase of signal. Where was phase of signal embedded? It was again a part of complex amplitude. Okay? Your complex amplitude was 4 times E j pi over 4. So the complex amplitude defines A, the maximum value of the envelope, and it also defines the phase of the signal. Then you have this term, this number 5. So we have discussed this, we have discussed this. The number 5, what does it correspond to? So you see this 5 is here, and this is nothing but angular frequency. and this is same as 2 times pi times f. Okay. And where did this 5 come from? It came from complex frequency. Complex frequency was defined as minus 1.1 plus 5j. So, the frequency, angular frequency is nothing but that 5, it is coming from there. And finally, you have this minus 1.1, okay, which is this thing. Where is it? What does this imply? It tells you how fast this green curve is decaying. So, this is rate of decay. And where does this come from? It also comes from complex frequency. So, complex frequency influences two things. One is the angular frequency of the system and also the rate of the decay, and the complex amplitude, it influences two other things, and those two things are envelope's maximum value and the phase of the signal. So, this is important to understand, because when you do measurements you will come across some of these terminologies and parameters, and you should be able to relate to these parameters. The second term I had mentioned is known as transfer function. Transfer function. And a lot of times we write it as h of s. S is your frequency. Okay. So, what is transfer function? It is basically, first thing is, it is a mathematical representation mathematical relation of a system's response with respect to the stimulus. This is the first feature. What does it do? So, suppose I have a motor and I throw in some current. So, what is the stimulus? The current is the stimulus. What is the output or the system's response? The motor is rotating at some frequency. So, it is a relation which connects the stimulus or the input to the output, which or the parameter in which I am interested in. So, this is one. But then this transfer function is only applicable for time invariant system. Time invariant linear system. So, it is not invalid for time changing system. What is time invariant system? So, once I, again to take the example of a motor, if I excite it with some voltage, then initially the speed of the motor is 0, and then it slowly or within a small finite amount of time it increases and becomes stationary. The speed becomes constant if constant current is flowing through. So, then the system's performance is not changing with time. It is either harmonic or it is a steady state system. So, that is what is time invariant. If it is fluctuating up and down or arbitrarily fluctuating, or if it is a transient, if it is not in a steady state, if it is in a transient state, then this transfer function is not applicable. And the other qualification is that is only valid for linear system. So, what is a linear system? In general, what it means is that if I double my input, then my output also will proportionally go up. So, whatever is the proportional increase, there is also some correlation between input and output, and that relationship is a that of a straight line. It may not be double, but it may not be, but the factor between change in input and change in output is constant. So if you plot the input and output on a XY graph, you will get a straight line. And so this is the case. So example. So we'll take 2 or 3 examples, things will become clear. So first we'll take the example of an amplifier. Okay. So what, amplifier, what I am giving it is some input okay, and I am measuring some output. So let's say I am exciting it with some voltage. I am providing an input to it, and it is running on some power source also, and I am measuring the output voltage to it. So then my transfer function, and it will be a function of frequency, it will be output, and if I am interested in how much voltage it is generating, then it will be in volts, and it will be a function of frequency divided by excitation voltage. So here the ratios, the input and output quantities which are being measured are same voltage. So this is a non-dimensional value which changes with frequency. So this is one example. The other example could be, I could have a spring mass dashpot system. So I have a spring mass dashpot system, mass is m, damping is c, stiffness is k. I am exciting it with some force Ej omega t, okay, and I am interested in finding out how much it moves. So let's say it moves by some amplitude x naught Ej omega t. Then my transfer function, the excitation or the stimulus is being provided by f naught. So here, and it changes with, it can change with omega. So this could be a function of omega, and that is basically, so stimulus is from force, and what I am measuring is the displacement. So x naught, which is a function of s, or actually omega here, divided by f naught omega. So in this case, the units will be meters per Newton. So transfer function does not have to be necessarily unitless. A third example could be, I am having a loudspeaker, and it's getting excited by a voltage source, and the voltage can change for different frequencies, and what I am interested in measuring is how much sound pressure level it is generating, the loudspeaker, and I can measure it in SPL, decibels. So in this case, the transfer function will be decibels per voltage, and again this could be a function of frequency. It could be complex frequency or actual omega. But the most important thing to remember about such functions is that they are valid only if the system is in steady state, and second, if the system is linear. Both of them have to be true. So that covers my coverage of these two concepts, transfer function as well as this complex time signal, and I hope you had a wonderful day today. Thank you very much, and we will meet once again next week. Thank you. Bye.